So it's lovely to welcome everybody to the Hertford Astronomy Group for our November meeting. Format of the evening after these announcements is we've got a presentation about the forthcoming night sky. Following that, I'll hand over to Jerry, who will introduce this evening's speaker. Jane is going to speak for about an hour, and there'll be an opportunity to ask questions. And for the questions, if we could ask that you type them in through the chat line, then that way we can field them correctly and in some sort of sensible order. Following the questions, I'll come back to myself, and you may remember from our September meeting that we had some visitors from Argentina, and they're hoping to join us again tonight and give us an update on their progress with their project about bringing astronomy to the masses in Argentina. So let me see if we can get some common sense out of my computer and start off with the night sky. Okay, so the November highlights. Martin is unfortunately indisposed at the moment, so he asked if I could take this section, which I'm very happy to do. So the November highlights, something to get out there. The November sky is really exciting. There's lots of things going on at the moment, and I'm going to give you a little bit of a taster by talking about some of the planets, the stars, star clusters, galaxies, things which you can get out and have a look at. They're all visible. Some are easy and some are a little bit more difficult. So there should be something there for everybody, and we'll make a start by looking first of all at the planets. If you look towards the east in the evening, this will work. You can see the bright planet of, there's a definite orange tinge to it. I know with a lot of astronomy, you've got to use imagination, but if you look at that, it really does shine out. And there are 3 missions at the moment heading towards Mars, all launched in the summer, end of July, start of August. The United Arab Emirates have got an orbiter on the way there. China have got an orbiter and a lander. And the USA have got a terrific lander going there. And they're all due to get there end of February, start of March. So Mars, lovely planet to have a look at, and certainly is going to hit the news in the spring. So out there, have a little look, and to say you can see it almost all of the evening as long as there aren't any clouds in the way. Let's move on to our next slide. If you look towards the south, you can see a very bright Jupiter shining at you. I was out last night around about, I guess around about 5, 5:30, and looked towards the south, and it really is bright. And by staring at it and looking slightly to the left, then you can also pick out that Saturn is there as well. They're not going to be particularly great through a telescope, but that's because of the atmosphere. To see anything that's that low in the sky, the image has got to travel through a lot of atmosphere, and so any turbulence is going to really show up in your instruments. But don't let it stop you. Get out there and have a go at it. Now, those people who like a challenge, we've got Mars here, and if you go this direction, then you will find Venus, and if you go similar amount in the other direction, there's Neptune. So for those of you who want a real challenge, have a go at doing that. From about 8 o'clock onwards is probably the better time to get that. So you've got a little bit more contrast, darker sky to have a look at. Obviously, that depends where you live. Now, early risers tomorrow morning, if it's all nice and clear, you'll be able to see this rather nice alignment of the moon, Venus, and Mercury. That's about 6 o'clock in the morning. Don't be put off by the size of the moon in the image, which is on the screen. It's a very thin crescent. Venus should be pretty obvious to see. Mercury will be the challenge. So those of you who like a challenge, have a go. You'll only have around about 15 minutes to be able to see it before sunrise comes along and starts to spoil the view, giving no chance at all of seeing Mercury. But if you can find Mercury, that's a really good one to have a go at. So all the planets are around at different times, but they are there if you want to see them. So let's move on then from the planets to the stars. And what have we got in the star department? Okay, well, in the early evening, we've got the summer triangle of Vega and Altair, with Deneb being the most overhead. Now, Deneb is the tail of Cygnus, the swan. And Albireo, I think we can just make a click and get that. It's going to be the eye of the swan. Can we show those? Yep, there's Albireo. And if we move back from Cygnus's tail, we will reach a constellation that looks a bit like a house drawn by a child. And this is the constellation of Cepheus, or Cepheus, however you want to pronounce it, the king. It's in that area. And you might just be able to make out if this was a child's drawing of a house. There's the roof. And there are the sides of it. And the reason I'm highlighting that one in particular is because Cepheus is the target in Terry's Sky Notes. Terry's Sky Notes is a regular feature on our website, and Terry writes a bit about constellations or things to be looking for. So if you want to find out more about Cepheus, go onto the website and look up Terry's Sky Notes. You can find that heartsastro.org.uk. Now, star cluster. If you move from Cepheus through Cassiopeia, you come along to the star cluster of the Pleiades, one of the most beautiful ones in the night sky. Seven Sisters, or Messier 45, is probably the most famous cluster of stars in the night sky. It's a cluster of thousands of stars that all formed from the same giant cloud of gas about 100 million years ago. Even in the most polluted areas of the country, you should be able to see a handful of stars, I should say light polluted areas of the country. You should be able to see a handful of stars huddled together on a clear night. Let your eyes become light adapted, and you might be able to make out up to 10 if your eyes are good. Train some binoculars or a telescope on them and be prepared to see one of the most beautiful sights in the sky. And I think that picture that we got there from Steve is really terrific because it's captured nebulosity as well as the stars. If you've never seen Pleiades, well, you don't know what you're missing. Really worth it. Okay, and the galaxy now. Well, we're going to look at the Andromeda Galaxy, and to find it, there are a couple of ways. The one that's on the screen at the moment is using the part of Cassiopeia, the right-hand V of Cassiopeia, which points straight towards it. Go down about 2.5 times the distance, and you'll find it. 2.5 distance the size of the V. The way I was taught to find it by a friend, Roger O'Brien, who gave the September talk, was to start at the square of Pegasus. Start at the top left-hand corner, go along 1 star, 2 stars. Now make a sharp right, do a right angle turn, and go up 2 stars, and you get to the same spot. And that will bring you to the Andromeda Galaxy. It's a lovely picture there. You can just about see it if the sky is dark. You've got good contrast. You could just about make it out with the naked eye. But you can put a pair of binoculars or a telescope onto it, and you'll get something which is about the size of a full moon. What's strange about it? Well, there's lots of things strange about all sorts of things out there, but this is the only object that isn't moving away from our galaxy, Milky Way. In fact, is heading straight towards us. Is due to collide with the Milky Way in about 4.5 billion years' time. So I wouldn't worry about it too much. When that collision occurs, it's very unlikely that stars are going to hit each other. Only about 1 or 2 will probably end up in real collision. So I think from that we can understand that space is pretty well named, isn't it? So that's the end of my little bit of a talk. I'd just like to say thank you to Steve, Michael and Stellarium for providing the pictures, and to encourage all the rest of you, if you do get a chance to take some pictures, drawings, whether you use a mobile phone, a pocket camera, or something a little bit more sophisticated, do send them along. We love putting them on the website for people to share and see how you've done it, and to encourage people to do it. So that's enough from me. Let's get back to the main screen, and I hope you can all see us there. I'm now going to try and find Jerry's moniker and unmute him. You're unmuted, Jerry. Okay. And Jerry, over to you if you'd like to introduce tonight's speaker.
Thanks very much for that tour of what we can hopefully see in the night sky. Of course, we always have to include that word, hopefully, because it depends on whether we are watching the sky or watching clouds. But something I would just mention, though, Alan's mentioned Cepheus or Cephas, who was an Egyptian king, and who was the wife, whose wife was Cassiopeia. That's the only husband and wife in the night sky, the only pair. So looking up at the night sky was a major feature of our main talk last month, when we heard all about Tycho Brahe, clearly the most diligent and accurate observer in the era before the invention of the telescope. And it was his observations which led his assistant at one point, Johannes Kepler, to deduce exactly how the planets move around the solar system. So it's only fitting that we should have Jane Clark with us tonight to talk about how you can actually move on from that, from making observations to actually calculate planetary orbits. I've got to say that when I read that description of her talk, I thought, that's it. We really got to hear about this. I mean, this is something that I'm sure a lot of you are going to want to try out for yourselves. So without further ado, I'll hand over to Alan to share Jane's screen, and let's look forward to hearing how you can measure planetary orbits, asterisk, subject to clear skies.
Right.
Thank you very much, Jerry, for that introduction. Jane, I think you should be able to take command of the screen. Yep, that's fine.
Okay, right. So, good evening, everybody. What I intend to talk about today is how you can measure the orbit of a planet. I was given a telescope as a 50th birthday present 14 years ago. And despite a vague interest in astronomy before that, I didn't do anything about it. And once I got this telescope, that was it. Bye, everybody. I'm out in the garden. I was just immediately and hopelessly hooked. And I joined an astronomy club. And I began to notice that the people in this club knew a lot more than me about cameras and telescopes and all that good stuff. But that I was noticing a few things that they weren't, and I don't think they quite knew what to make of me. So I hope you might manage to make a bit more of me than they did, but we'll give it a go and see what happens. Where are we? There we go. Yeah. So what I'm going to talk about first is what Venus teaches us, and observing Venus teaches us that it orbits the sun. We can find out what its orbit is, and we can find out how far from the sun it is. Then we'll go on to superior planets and measuring their orbits. The superior planets in the solar system are Mars, Jupiter, Saturn, Uranus, and Neptune. And then finally, we'll have a look at Jupiter's moons, because you can play some quite fun games with those. So the thing about planets is that there's a starry background which travels around in the northern hemisphere. It appears to go from east to west, but of course it's the Earth moving from west to east. But relative to that starry background, and the stars are about 1 million times as far away as the planets, the planets seem to move. And here's a picture. You can't say I don't give you recent results. That was the 12th of October. By the 15th of October, relative to the starry background, Mars had moved to there. So that's the kind of speed you can expect planets to move at. And Mars will move fairly fast because it's not so far away. So how do we know that Venus orbits the sun? Well, what Venus is typically a morning or an evening star. I mean, as Alan said, it's a morning star at the moment. There it is in this picture here. It's never far from the sun, never visible at midnight, but it is very bright. It's the third brightest object after the sun and the moon, which makes it, when it's around, it makes it easy to recognize. And through a telescope, these are the dates shown. In fact, that's the one that I took 5 minutes after I took the photograph that I just showed you there. And it down here, I hope you will believe me when I say that it's gibbous. It's more than half phase. Up here, I hope you'll believe me when I say it's crescent. Yeah. And somewhere in between, it's a half phase. Now, if you postulate, I mean, somebody mentioned earlier about if you believe Ptolemy's theories. Well, this is a diagram of the sort of Ptolemaic view of the universe, where this time we've got the Earth in the middle, the sun's orbiting the Earth, and then further out, Venus is orbiting. And in that system, it goes round and round in epicycles like that, because that's the only way you can reproduce in that system the apparent motion of the planets in the sky. So whatever you do and however you look at Venus, when you look at it like that, there, the light side of Venus, which of course points to the sun, is always at more than half phase. There you can see more than half of it there and there. So it will always be gibbous. If, on the other hand, you again make Ptolemy's postulate that the Earth's in the middle, this time the sun's going around the Earth, but it's further away than Venus, Now, the bright side of Venus always points to the sun, because that's where it gets its brightness from. So if you look at each of these, it's always going to be crescent. It's never gibbous. And that was what Galileo found in 1609, 1610, when he first pointed a telescope at Venus. And he, in fact, sketched a diagram much like this. And you can see that it's sometimes gibbous and sometimes crescent, and just for a brief period in between, it's a half phase. So that is how we know that Venus must orbit the sun, not the Earth. And the debate between the kind of Copernican and the Ptolemaic systems, it was the invention of the telescope that settled that debate. And after that, the Ptolemaic view of the universe rapidly faded away. And that's very typical for all sorts of astronomical discoveries, and indeed scientific discoveries generally. That is the rate determining step is always what you can observe. The theories very quickly catch up with what the observers find. And, you know, it might be within 2 or 3 decades, but on the scale of things, that's pretty quick. And so you can theorize all you like, but if you haven't got some observations to test your theory against, science really doesn't advance. Now, half phase, incidentally, the word dichotomy means half phase in its original meaning, at any rate. So I mean, this was the point about a year after I was first given a telescope. By this time, I'd bought a second-hand 8-inch one on eBay and was just learning to take photographs. So they're pretty rubbish photographs, really. But I think you'll agree that Venus is somewhere around about half phase there. And I looked at that and I thought, okay, if that is at half phase, then it follows that the angle between the Earth, Venus, and the Sun there must be a right angle. Mm-hmm. And so we know that's a right angle. We know that distance is 1 astronomical unit. And so you need, if you remember your high school geometry, you need 2 sides in an angle or 2 angles in a side, and you can solve the entire triangle. So what I want is either the angle B or the angle A. Well, I thought I could have a go at measuring the angle A there, which is the angle between where the Sun is and where Venus is. And what I did, I mean, I tried it with protractors and a pair of rulers first, and that was just hopeless. So what I did was I made this very Blue Peter-ish gizmo. I used a computer-aided drafting system to draw myself an angle scale there. These bits of cardboard are, in fact, if you send your trousers to the dry cleaners to be cleaned, they come back with one of those on the coat hanger to stop your trousers falling off. So that's what those are, because they formed something that I could look along. Cut a hole there and there so I can see what the angle was. And there's basically a drawing pin in there at the eye location. So off we go. And what you do is you very close, I mean, if you try and do this during the day, it's hopeless because the sun just blinds you and you can't see anything for another 10 minutes. But right at sunset, when the sun is quite red, it doesn't blind you quite so much. It does a bit, but not quite so much. And Venus is beginning to appear, and with a bit of practice, a bit of skill, you can see it. So what you do is you look at Venus, and then you look at the sun, then you go blind for a minute, and then you look back at Venus, and it's a bit of a faff, but you can eventually get measurements. And I got, on the 29th of May that year, I got 2 measurements of 46 and 47 degrees. So let's average those to 46.5, do my trigonometry, and I get that the Sun-Venus distance is 0.725 astronomical units. Now, the published answer is 0.7233 astronomical units. So for a bit of really Mickey Mouse measurement, I could actually get the distance from the sun to Venus in astronomical units. And this was the point at which I began to be encouraged to believe that actually this stuff's not rocket science. You can do it. And this is the point at which, you know, the people in this astronomy club just looked at me, gone out. But it's not that difficult. And it, you know, it's basically GCSE maths that you need and a bit of wit to measure it. Now, was this a fluke? I promise this is the only equation I will show you in the entire presentation. And you can look at it one of two ways. You can sit in the sun's frame of reference and say that the sun's gravity is providing the centripetal force which pulls the Earth around. In this case, I've modeled a circular orbit. And mass times the angular frequency of rotation squared times the radius is the centripetal force. And Newton's law of gravity is a constant times the mass of the sun times the mass of the planet, which in this case is Venus, is equal to the 1 over the square of the distance from the sun to Venus. Or you can look at it another way in the planet's frame of reference and say that in that frame of reference, you're in free fall because the gravity force is exactly balanced by the centrifugal force. You end up with the same maths. Anyway, take that equation, play around with it a bit, take that R down there, and you get G, the mass of the planet cancels. So G big M over R cubed equals omega squared, but omega is 2 pi divided by the time period. So you've got a law there that says that the radius cubed is proportional to the time period squared for a circular orbit. That's also true for an elliptical orbit if you replace radius with the semi-major axis. So you can use that law and plug it in. And I'm going to, at this point, you know, the clever scientific thing to do is predict what's going to happen in the future. So I'm going to say that given that I had the position of half phase within about 5 days, that on the 29th of October that year, plus or minus 5 days, we're going to see the Venus is at half phase again. So how did I do? Well, there's my May and June pictures, and here's my October pictures spilling over into November. So somewhere around about 30th or 31st of October, there's a half phase, is what I'm saying. So I'm about right. And on the 30th of October, again, using my Mickey Mouse piece of kit, I got 4 measurements this time, 46 degrees, 47, 47, 48. That gives me 0.73 astronomical units compared to 0.7233. So, you know, I've shown that it's not a fluke. It was a result that predicted when the next half phase would be. And I get roughly the same distance between the sun and Venus. So for a bit of really Mickey Mouse physics, well, I claim my round of applause. Thank you. Now, which way round do the planets? I've also shown that the planets both orbit in the same direction. And I know, because if they counter-rotated, the second time it was at half phase would have been sooner. And I know from experience that in spite of drifting east and west a bit, they basically moved to the east, all of them. So that means that actually, whoops, the planets all go around the sun in the same orientation, which if you look down onto the North Pole of the sun from some magic spacecraft that you've got up there, then you'll see them all going from west to east, which would then be anti-clockwise. Now, transits of Venus, they're not very common, are they? Sorry, I'm not doing very well with this. They're not very common. That's how many transits of Venus there have been in the modern era. The 1631 one was not observed. First one to be observed was 1639. And it was Edmund Halley of comet fame who made the prediction. And then the next ones were 1761, 1769. They always come in pairs 8 years apart. 1874 and 1882, and 2004 and 2012. And I think that was the one that Captain Cook saw, 1769, in Tahiti. So there've been 5 since then, and I've seen 2 of them, as I suspect many of you will have as well. And if you missed them, I'm sorry, the next one's going to be in 2117. Now, one of the other curious things about these is that not only do they come in pairs, but the dates of the those are December ones, those are June ones, those are December, those are June, but they're pretty much the same dates in December. See, 6th and 9th, 7th and 4th, 6th of June there, 3rd and 4th of June, 8th of June, and 5th and 6th of June. And that's not coincidence. It's because the ratio of the periods of the orbits of Venus and the Earth are about 13 to 5. So for every 13 Venus years, there's 5 Earth years. And that's what drives this regularity. Now, the 2012 transit, I found this by poking around a bit. I found this website. It's not there anymore, I'm afraid, because I checked today. And in this part of the world, the entire transit was going to be visible. Partly visible there, partly visible there. So there's no point in spending a fortune traveling to those places. So you could go to Hawaii, or you could go to China, or you could go to Australia. And what this website shows is actually the probability of cloud. And it's that in China, it's the northern monsoon season in June. So it's likely to be cloudy. And in fact, you know, the astronomy magazines were selling highly expensive trips to China, and they all got clouded out. Whereas down in Australia, you know, basically it was going to be likely to be cloudy. And the further north you could get in Australia, the better, really. So it was Australia or bust, and that's where I went. So we found the sun. I thought there would be loads of people there, see, because the last time I went to see an eclipse, there were just loads of people there with telescopes along the path of totality. But anyway, I only met one other astronomer, this woman, Melissa. And nobody else. Melissa took this picture of me there. But what you did see, we started in Alice Springs, but it was cloudy there. But we could see clear sky 20 miles north, so we just drove up this road until we got out from under the cloud. They have these road trains in Australia like that, and I paced this one out. I mean, I measure everything, me, and I paced this one out. It was 1/4 mile long. So, you know, when it says no overtaking on Australian roads, basically just don't. So I've got the times here in Universal Time. Of course, midnight Universal Time was daylight where I was. So there's the first picture of the transit, and it moves across over a period of time to there and eventually to there, and then it's gone. You don't see it anymore. Now, you'll notice that there are some sunspots there. And in fact, you have to reorient your photographs so that the sunspots give you your opportunity to reorient the photographs, so that the sunspot pattern is pretty much where it was. But if you look again closely at, say, that sunspot or that pair there, you will see that actually the sun has rotated significantly during the 7 hours or so of this transit. It's gone around a bit more there and a bit more there. So if you want to measure the length of an astronomical unit, because I told you so far that Venus is 3/4 of an astronomical unit and the Earth is 1 astronomical unit. And celestial mechanics, for the most part, finds relative distances between things. It doesn't find absolute distances. You need something else to do that. And you need 2 simultaneous images from different distant places on the Earth's surface. They've got to, this is images of the Venus transiting the sun. They've got to be simultaneous because everything's moving. Venus is moving, the Earth's moving. The Earth and the sun rotate quite noticeably during the time of the measurement, because it was 6 or 7 hours, don't forget. And the light moves as well. I mean, time of light travel from the sun to the Earth is 8 minutes. It's 6 minutes from the sun to Venus, So it's 2 minutes from Venus to Earth. So your two photographs have to be absolutely simultaneous. Otherwise, you start having to do a relativistic calculation. And the European Space Agency, in fact, they had two expeditions. One to this place, Svalbard, up in the Arctic, in Spitsbergen, and well, Spitsbergen is one of the islands of Svalbard, I think, strictly, and one to Canberra. And I smugly thought that my judgment was better than theirs because it wasn't that sunny in Canberra. But anyway, from their website, I was able to get these two images, which are taken absolutely simultaneously. They're like that. So you do get a bit of parallax between the two. The question then is, can we exploit that to see if we can get a distance measurement? Now, what I did was I am quite fond of using a computer-aided drafting system known to engineers as a CAD system. Import your photograph in, and then you can, the tools of the CAD system will enable you, I mean, to get a circle around that, you pick any 3 points and they define a circle. So you do that enough times and you'll, with a bit of practice, you can get quite an accurate circle like that. And once you've done that, and you do the same there and then, do it a few times, as you can see, I've done it a few times, and average the results and all the rest of it. And then, so from my these are their pictures, so I can get the parallax measurement from those. From my pictures there, which is a bit sharper than theirs, until you start to look at Venus, then it's not so sharp. Their pictures of Venus were sharper than mine. You see, again, you do 3 measurements like that, average them. I know the size of the pictures, and in my own picture, I also know how many pixels there were and stuff like that. So I can work out that, in fact, I've got a solar angular diameter of that in radians, 9.39 plus or minus 0.0095 milliradians is the sun's, it's the sun's diameter in radians. So I know that, and then go back. You do a bit of geometry like this, because this is the basic geometry of the situation. You've got 2 observers there and there on Earth. You've got planet Venus there. Planet Venus is in reality the same size as the Earth's nearest making a difference. But it's drawn like this. But the sun would be huge on this scale. So a bit of artistic license is allowed, I think. But essentially the idea is that angle's the same as that angle. Do a few calculations using basically GCSE trigonometry. And you've got those are what you see from those. And I've put in that distance there is 0.725 times that distance. So the radius of the Earth's orbit divided by the radius of Venus' orbit is that. Plug the numbers in. Remembering that that's my basic geometry again. That's where I got my figure of 0.725 astronomical units from before. And that's the value I got. In kilometers, I got 1.53 plus or minus 0.02 times 10 to the 8 kilometers. And the published value is 1.5 times 10 to the 8 kilometers. In other words, 150 million kilometers. So I'm 1 to 3% high. So again, you know, the equipment that they took to Svalbard and to Canberra wasn't a lot different from the equipment I had. So, you know, they didn't hike really powerful telescopes there. So you can get that. And I checked today, the ESA's website of that expedition is still there. So if you want to do the measurement, you can. Now, let's talk about superior planets. An inferior planet is a planet that's nearer the sun than we are, like Venus. A superior planet is further from the sun. Now, this is nothing it's not a value judgment. It's not like saying that Hertford is a better place than Harlow. I mean, I can't see why anybody would think that, but it's not. It's just more a position in the solar system. And this is the kind of equipment that you could use. I mean, I started out just taking a common or garden but high quality webcam like that, plant it on a tripod and let it sit there and shoot footage. And then, are any of you familiar with a piece of software called Registax? Yeah, I get 1 or 2 nods. Yes. Basically, each frame will have tracked a little bit across the sky, but Registax will stack them and align them for you. So you can do that. And if you do that, you get about the same accuracy that Tycho Brahe got in the 1580s or whenever it was. Slightly cleverer version of that is that I put an eyepiece in front of this and then plug it in through the eyepiece of a telescope. So I've essentially got eyepiece projection. Doing it that way, sorry, you get half a degree with that. That's the one that's as accurate as Tycho. You get half a minute doing it that way. But if you put a DSLR like that with a telephoto lens, all that's just lens hood there, piggybacked on your telescope so it tracks with your mount, and then you could either use a separate guiding system or you could use the telescope itself to guide with a program like PhD2 guiding. Then you can get, well, when I first tried doing it, I was guiding on the planet. And the limitation is how well you guess where the center of the planet is doing that. And I could get about 6 arc seconds. But since then, I've moved on to using a secondary guiding telescope and guiding on stars, not on the planet, because the planet moves. And the other trick that I've learned is if I expose for 4 minutes to get the starry background to measure the position of the planet, then beforehand I do a half-second exposure, and afterwards I do a half-second exposure, because you then get the planet well defined as opposed to overexposed, and average those 2 positions. And doing that, I can get within 1.2 arc seconds of published positions. That's what guiding is. The idea of that is that you have a secondary camera in addition to what you're trying to take your pictures with. You pick a star in there like that and click on it, and the software puts crosshairs there. And what it will then do is send commands to your mount to fine tune the tracking of the mount to keep that star in the crosshairs. And that's really what you need to do to get accurate pictures without trailing stars. And the software you do it with is free. It's called, I mean, there were several around when I first started doing this 10 years ago, but since then, a new version of PhD stands for Push Here Dummy, to make it easy, allegedly. And that software, it's vastly superior to whatever else is out there, and it's pretty well taken the market now in freeware for guiding. Now, as you go further from the sun, the superior planets move back and forth with respect to the stars. That motion's called an epicycle, and it goes along there over a season, around there, and back down here, and then goes off. And that was 2009 to 10, which was a winter opposition, so you had Cancer there and Leo there. Wait a minute, I think somehow it's just a picture out, didn't it? No, it hasn't. Go forward. Now, Mars, before, during, after its closest approach, because it's further from us, we never see it crescent. We'll see it either full like that, when the Sun, the Earth, and Mars are more or less in a straight line, and you'll see it gibbous like that when it's further away. The relative sizes tell you that Mars is further away there and there than it is there. Another thing to say is that you can get a handle on how coplanar the orbits of these planets are with the orbits of the Earth. This, in the season 2008-2009, was me tracking the asteroid series as it went through its epicycle like that. And the orbit of Ceres is at about an inclination of 10 degrees to the orbital plane of the Earth. And that's what it looks like. It looks like a really open epicycle. Saturn, the previous year, was around about, that's Regulus, Alpha Leonis, was around about there as well. And it went down there, up there, and down there in almost a straight line. So that is telling you that that's, hardly any degrees tilted from the Earth's orbit compared to 10 degrees. So that's how you can know that you've got a fairly coplanar orbit. So how do we ride one of these epicycles, find out what's going on? Well, the geometry is basically simple. And once again, it comes down to triangular geometry. So in this game, you've got to know your triangle geometry. But it's, I would say that anybody with an A level in maths could do this. You've got the sun there, the Earth there, and your superior planet up there. Now, what you actually do is you assume that they're coplanar and circular orbits. And if that assumption proves to be rubbish, we'll find out. You solve for the green triangle, and it needs one go of the sine rule. I mean, you've probably all forgotten that, with extreme relief when you passed your GCSE maths. It's the sine of that side over the sine of that angle over the length of that side equals the sine of that angle over the length of that side equals the sine of that angle over that angle over the length of that side. That's the sine rule. So use that once. And there's a cosine rule as well, which says that squared plus that squared equals twice that length there is twice that one times the cos of that angle. So you use that as well once. The algebra gets a bit messy, but it's nothing conceptually difficult about it, I don't think. And there's, you could, if you don't like doing algebra, you can feed it into, I think, a website called Wolfram Alpha for free these days. Feed your equation in and it'll solve it for you. And if you press the right button, it'll even print out you working. And what we're actually observing is that angle beta, because when it's there, we look along that line to whatever stars are up there. And when it's there, we look along that line to the same stars. So what changes that we observe is that angle beta. In other words, the angle to the planet relative to the stars. But we also need to know the position of the sun. And by taking photographs of the starry background, you can get that. Can you get a photograph showing where the sun is relative to the starry background? You can do that on a very few occasions, and those are known as total eclipses. But most of the time you can't. And at this point, I had one of those, oh my goodness moments. What am I going to do about this? But I didn't fret for long. I had a brainwave, as you do. And yeah, like I say, you photograph the planet as often as you can like that against the starry background. And there's Mars in Taurus. There's the Pleiades just there. And here it is. That was in August. By the following April, it's found its way into Gemini. There's Castor and Pollux. There's a full moon in this one as well. And that's, what's it called in Auriga? The bright planet Capella. Bright star, sorry. And this is the kind of kit that I was using then. There's my 8-inch telescope, like that. It's hooked up to a camera. That goes to my focusing motor. And it's a real boon that you can actually, for once, get a white cable, because these black ones in the dark, you trip over them all the time. Yeah, they will make them black, won't they? So the webcam's connected to the laptop. This is an equatorial mount. The idea of an equatorial mount is one axis points at the North Pole, and you point accurately enough to correct for the star Polaris not quite being at the pole, and then you counter-rotate against the Earth's rotation. That's how the mount tracks. And then, I mean, when I did all this, the constraint I set myself was that, yeah, I was doing this to write a book and it had to be doable with A-level maths. That was the constraint. So you've got an unknown planet there, 2 known stars from a catalogue. You just do a bit of, so again, it's triangles and knowing your triangle geometry is what it comes down to. It's not even particularly messy, the arrangement for the algebra for that. I mean, I make a ghastly assumption that that part of the sky is small enough that you can use a kind of Mercator projection of it rather than having to take spherical geometry into account, which means really that the stars have to have similar latitudes or declinations for the method to work, but that's not a problem. And then again, I feed them into my trusty computer-aided drafting system. You draw circles around those, everything freehand, which with a bit of practice you can do quite well. And then and you probably do it more than once, because one of the things you can do is you can set layers in the CAD system. So if you do it 3 times, you've got 3 values of each of these angles. You use those angles back in this, and then you've got it. Now, what do we do about the sun? You can't photograph the sun against the stars. So if you can't use kind of, you know, high principle, you've got to use low cunning instead. And so I had to think, what do astronomers know? And the answer is that if you are a practicing observer, you will basically plan your life around sunrise and sunset times. So you'll know them and be very aware of them. And it's easy enough to find a sunrise and sunset type table for your location. So the thing is that it's sunrise and sunset, but only at those times the sun is perpendicular to your local zenith. And you can actually exploit that fact to do some geometry and solve for the coordinates of the sun. So that's what I mean about low cunning. Just think of a clever method of doing it. And you need to calibrate this. You need one opposition event where the sun, the Earth and the planet are in line. And I used Saturn on the 25th of February 2008, and I got a photograph of Saturn within 12 hours of this. So that gave me a diametrically opposite position to calibrate my calculation with. And how well did I do? Well, comparing it to what the US Naval Observatory's website says the position of the sun is, those are the thin lines. The dotted lines are my calculation from sunrise and sunsets tables, and you get extremely good agreement. And I don't claim that I measured the sunrise and sunset every day where I then lived, which was in Kingsland in Norfolk, but every once in a while I would, you know, so that I knew that these tables were correct. Oh, there was the photograph I was looking for before. For Mars, using a static webcam, that's the kind of tracking you can get like that. And it's okay, it's not brilliant. And I got a radius of Mars orbit of 1.68 astronomical units and an opposition then, which was probably about 10 hours from the actual opposition time. So I got a reasonably good result. There again is my picture using a more sophisticated technique. These positions, the worst of them are there because Mars is moving the fastest there and there. They're within about 6 arc seconds. I didn't check them all, but I checked enough to convince myself that the rest of them were at least that good. And 6 arc seconds, remember, an arc second is a 60th of an arc minute, and an arc minute is a 60th of a degree. So it's a pretty small angle. So we're accurate to 0.0017 degrees in positioning Mars. That's what I got for Jupiter. This one I used a slightly different method from the others in that I've used Excel to fit, there's basically a polynomial through there, like that. And from the the fit of the polynomial, you get an equation like that. It's a 6th order polynomial, 6-degree polynomial. Differentiate that, put it equal to 0, and that tells you that and that are the positions where the planet turns round. There's a method in this book which you could download off the web, which allows you to turn that into a radius of the orbit in astronomical units if it's circular. So that's what I got. I got 5.13 astronomical units and an orbital period of 11.63 years. I think the actual period is about 11.9 years, so it's not bad, considering some of the ghastly assumptions I made on the way. So that's that one. Where's the next one? Saturn. That was using my standing webcam. Then I switched to putting the webcam through the telescope. It gets the data get a lot better at that point. I used a Monte Carlo method to solve those. What a Monte Carlo method is you try 32,768 randomized trials of values for an orbit and pick the best. And you use, essentially my measure of that was a least squares deviation from a predicted value. So you get the one with the least squares, and then you pick that off. So I got Saturn at 9.27 astronomical units with an opposition then. And you may recall that that's within 12 hours of the actual opposition, because I told you I'd photographed it close to that. So you use the period squared over the radius cubed over equals a constant times the period squared, and you can get the time in years. Unfortunately, I forgot to print it on there, but it's not a bad value, because it's a little bit low, if anything, because Saturn's about 10 astronomical units away. Doing the same thing with Uranus. Now, Uranus is a bit harder to find because it's not as bright and not as easy to see. But I followed it over that time there, and I got it orbiting at 20.1 astronomical units with an opposition then and a period of nearly 90 years. That's a bit high. The actual period is about 84 years. So it's a bit rough and ready, but again, it's not a million miles off what it actually is. And finally, Neptune, I did. And that's the curve I got there. Again, used this Monte Carlo method, and I got 29.4 astronomical units and a period of 159.4 years. It's about 30 astronomical units, so that's not a bad value, actually. It's better than my value for Uranus. So summarizing those are the orbital radii that I've got, assuming that they're circular. Those are the published values. So the discrepancy for Venus is 1.6%, for Jupiter is 1.9%, Saturn is 4.2%, Uranus is 7%, and for Neptune it's 3.4%. Mars is not so good. And the reason for that is because the orbit of Mars is not very circular. And I'll mention in a minute what I'm doing about that. But first, first I'm going to have a drink. And then I'll go on to Jupiter's moons. Anybody who's ever taken a photograph of Jupiter knows if you overexpose it a bit, you get these 4 moons like that. And what I've done is used a computer-aided drafting system. Again, import the photos in and measure the positions of the moons. So using equipment of kind of, 2007 state of the art, which was my 8-inch telescope and a high-end Philips webcam, you had to take 2 exposures, one to get it like that, and one where you can see the climate bands on the planet. And you use the climate bands on the planet to orient the planet. and want to get the moons. So you keep doing that. You assume the orbits are circular, and what I did was just let's assume they're circular, see what happens. And in practice, I couldn't find any deviation from circularity in them, and it's really because Jupiter attracts a certain amount of stuff that floats around in orbit around it, and it acts as damping material. And you can show with a bit of a struggle that an elliptical orbit will damp to a circular one. So what we see is the projection of this circular orbit against the heavens. So the equatorial component of it looks like that. It's A times the cos of some frequency times time plus a phase angle. You can't do a least squares fit to that very easily because it's a transcendental equation. So again, I used a Monte Carlo method, which is just try it with a random number generator a bajillion times and pick the best one, the best fit. Now doing that, these are the orbits of Jupiter's moons that I got. The closest one in is Io, and you get that. Those were points there are where I measured it, and that's the cosine wave that I fitted through those points by Monte Carlo methods. And it's the next one out is Europa, which again there's relatively few data points and a wave fitted through it. The next one out is Ganymede, with again few data points, and you get a wave like that. And Callisto is even further out. Basically, I just kept this going for long enough to get one orbit of Callisto, and then I gave up. And the curious thing to note about the three inner moons is that whenever that one's up, that one is either up or down. And that's true every time. There it's up, there it's down, there it's up, there it's down, which means that the period of the magenta one is twice the period of the dark blue one. And then you get the same ratio between Europa and Ganymede. But every time that's up, Ganymede is down, and Europa is down, and every time it's down, Europa is down, but in between there's one up. So the ratio of Io to Europa to Ganymede is 1 to 2 to 4 in a resonance. So the orbits of those inner three are quantized like electrons around a molecule or an atom. But they're not quantized for the same reason. In the case of electrons around an atom, the electrons are in standing waves, and you have to have, to get a standing wave, you have to have an integer number of wavelengths. And that's why electrons can only exist in certain wavelengths in an atom or molecule. The reason for this is a very subtle second order gravitational effect where these moons pull on one another and pull themselves into this resonance. And once they've captured each other in the resonance, they just keep doing that forever. And as they do it, they are slowly moving further out from Jupiter. So Io moved out a bit and captured Europa, and then they both moved out, and Ganymede got captured, but they haven't moved out far enough yet, and it'll be billions of years before they do, to capture Callisto. So that's what's going on there. Now, you remember Kepler? I said that T squared, that's called Kepler's third law, by the way. T squared is proportional to the radius of the orbit cubed. And therefore, on a log-log plot, you'd expect a gradient for that line there to be 1.5. If you've forgotten about logs, don't worry. Just take my word for it, that that's what you'll get on a log-log plot. And I actually fitted that and got a slope of what, instead of 1.5, I got 1.504 plus or minus that. So I've demonstrated that Newton's law of gravity works for this system to within 1%. Because you need Newton's law of gravity and the law of centrifugal force or centripetal force, which was discovered by Cassini. No, not Cassini, sorry, by Huygens. Put those two together, that's how you get that. So I've demonstrated that that works on this system to within 1%. But I haven't run out of things you can do with these yet. there's still more. Well, first of all, here's some pretty pictures. With a better telescope, I got a 9.25-inch Schmidt-Cassegrain telescope at one point. So we've moved forward a few years now, and those are the kind of pictures I can get. There's Europa, there's Io, and there's Callisto. So the pictures are a bit better, and I can do it all off one picture. But now we've moved on a bit again. And in my backyard, I've now got an observatory, which I bought this off a retired woodworking teacher who had become too old to use it. And so his wife wanted the space back in the garden. So I got it for a song. And I've put it in my backyard, but I've got a good view from my backyard of the sky as well as the scenery. And that picture there was in fact taken at night. That's the moon, not the sun. So I'm quite well set up now, and I've got an 11-inch telescope in there. I mean, when I started this, I was on a low budget because I had a kid going through private school and no money. Now the kid is grown up, 30 years old, and about to buy a house, married, and all the rest of it. So, you know, I can spend money on what I want now, and I've got that. And that was the kind of quality of picture I was getting last year. I could see 4 moons quite easily on that and see the planet quite well. The planet itself is quite low in the sky over the next few years, so you're not going to get great pictures of the planet. But this summer, I bought a much better camera. I bought one of these ZWO Optics ones, and that's the planetary camera of the moment in their system, and you can get much better pictures with that. It's just a fabulous camera. And I'm really pleased with that. It was a very good investment in money. And you can see the red spot doing its thing there over a period of, what's that? That's nearly an hour. And that there's 2 moons, one there, which is slowly but surely getting closer to Jupiter. That's Europa. And you can see Io there, which actually is right going behind Jupiter there, and it's gone by that time. And you can also start to identify them by the color, because I don't know if you can see it on your screens, but Io is actually quite a bit redder than Europa. And so that, you know, you're not just identifying them from tables, you can see them. So anyway, I'm still taking pictures and measuring their positions. Now, what I've done is, last year it was exactly 1 Jupiter orbit since those pictures I took in 2007. And I don't know if you can cast your mind back to 2007, but that Gordon Brown had just become Prime Minister. Whether that's a good thing or a bad thing, I leave to your judgment. But then the flood started, and Gordon Brown was, you know, going around dealing with the floods and so on. And it just rained and rained and rained and rained in July 2007. Yet on 14 out of those 17 days, I managed to get pictures, because you only needed to see the sky for 5 minutes to get your picture. But anyway, if I carry on the same series using my more modern equipment to measure it, and again, it's the same thing, you only actually get a few measurements and you fit the lines between them. But everything, like the orientation of the plane that you see relative to the Earth, it's the same, because it's exactly an orbit later. So all, you know, the effect of the ellipticity of the orbit and all sorts of things cancel out. So it's a much simpler calculation. And basically, if you count orbits between then and then, counting is a perfect process, providing you do it right. There's no drift in counting. So I've just taken these curves here and counted the number of orbits I expect, because I'd already got a reasonable value for the periods of the orbits, and then essentially use the amplitudes and periods I got in 2007, tweak the period until you get a least squares fit on these curves here, and I pretty much did that by hand, because, you know, I mean, you could use an algorithm like you know, Gauss-Newton or something, but in the end I gave up and did it by hand. And now I can start to get, because of the number of orbits that have taken place, I can start to get periods of these things to quite astonishing accuracy. I've got 1 part in 166,000 there compared to the published value, 1 part in 150,000 for that. It's less accurate for those because I've counted through fewer orbits. But I can, if I've got that level of accuracy there, what do I want that for? Shouldn't I just get a life? Well, the answer is that actually, if you come to this diagram, I've got these 2 diagrams in a daft order in the presentation. You may have heard of a guy called Romer. He worked for Cassini in Paris. They were contemporaries of Isaac Newton. And the big problem they had in those days was trying to measure latitude. And, you know, it was an important problem for commercial shipping, which was becoming more important as Europeans started to cross oceans. And it, you know, it was also important because they basically didn't know how wide Europe was. Now, but one of the ideas they had was use eclipses of Jupiter's moon Io as a standard clock, because they had clocks that were quite accurate if you kept them in one place, but as soon as you moved them, you destroyed the accuracy. So Cassini sent this guy Romer, who worked for him, back home to Copenhagen, said, you go there and time them and I'll come here and we'll use that as our standard clock. Well, he was a bright lad, was Romer, because he noticed that actually, if you got that configuration, the distance is shortened if you got that configuration. But what he noticed was his clock was accurate enough that there was a 10-minute delay in the eclipses there compared to there, and a 10-minute difference there compared to there. And he realized, he was bright enough that he realized as a result of that, that light must have a finite speed. So my idea was, can you invert that experiment and get a measure of the astronomical unit? Well, the answer is yes, you probably can, but you have to be very, very accurate in your measurement of the period of Io. And you are talking 1 part in 100,000. So that's why I took the trouble to do that. Anyway, let me go back a bit. The next part of my future is the kind of methods that I've been talking about are what are known in the trade as angles-only methods, where you only know the right ascension and declination of the planet at any given time. And that's not, I presume Robin Scargill told you that Kepler basically had some range-finding technique that he used, where the Sun and Mars were in known positions, the Earth had moved around on successive orbits of Mars, and used range finding between them to get distances to Mars. Well, if you want to do it in one season, you can't do that. So what I want to do is use an angles only method over one apparition. And the methods that you can find in no end of books for working out the orbits of asteroids don't work. It worked when I tried Ceres, the asteroid, because that's not coplanar with the Earth's orbit, so you can look down on it and get some triangular information. And Gauss, among others, was very cunning in the way he managed to exploit the information in those triangles to get an orbit out. So I'm trying to find an angles-only method that works when the orbits are coplanar. The method I'm looking at the moment is by a guy called Hergé from 1965. I've looked at several others, but they're, you know, not easy to use. One method I looked at, you've got to teach yourself the way people did it before the days of vectors, which was spherical trigonometry. Standard textbook on trigonometry is dated 1888, and nobody needs to learn it these days, so they don't. The other method required quite a sophisticated understanding of statistics, more than most scientists possess, so I abandoned that. And I'm hoping that that will give me the orbit of Mars as an ellipse. And I've got a contract from Springer to write a book on that, which I'm due to hand in January. But also that same Hergé method, I hope, will give me an accurate orbit for Jupiter. And I've got an orbit for the Earth, which I did. Do you know what the equation of time is? It's the equation that relates solar time to mean time, because the solar time could deviate by up to a quarter of an hour from mean time. And there's an equation which is grandly called the equation of time that relates them. Well, you can back calculate from the equation of time, and you can get out of it the Earth's orbit as an ellipse, and you can get the obliquity of the Earth. And I got an eccentricity of 0.016. It's actually 0.015. So slightly high, but not very. And I got an obliquity, the angle it points like that, of 23 degrees. So I was quite happy that I got reasonably accurate Earth's orbit. And I got 4th of January for the perihelion. It's actually about the 3rd of January. So I've got a reasonable orbit for the Earth. If I can get one for Jupiter using this Hergé method, then I should be able to back calculate all this and get a method for measuring the astronomical unit where you don't have to wait until 2117 and the next transit of Venus. So that's what I'm playing with now. I should finish by telling you a little story of Roma. He was quite a capable guy, as I say. After he finished working for Cassini, he went back home to Copenhagen, and he became effectively the mayor of Copenhagen. And he became quite noted in Danish history because he put running water in around Copenhagen in somewhere around about the year 1700. And the other thing he put in Copenhagen in the year 1700 was street lighting. So the bastard invented light pollution. And on that note, I'll finish.
Thank you very, very much, Jane. There's an unexpected finish to that. Well, it's been quite a fascinating presentation. I've been taking down notes on that. You pinned me to the post on one thing when you've talked about observing the sun, because you've been talking about, well, all right, so including the sun in measuring angles from the sun to a planet. And of course, one way to do that, if you're not sending stuff to the dry cleaners, is if you can put a white light filter on your telescope and point that at the sun and note off your handset what the angle is, and then move over to a planet and note the angles there. So you
you can certainly do that. I mean, because with my setup now, I've got a program, CW something or other is Celestron's program for controlling the mount from your PC.
Right.
That'll give you quite accurate information on where you're pointing.
Yeah. The other
certainly do that.
Which I was going to mention is that you were talking about working back from the equation of time, but if you don't have the equation of time to start with, then you get a camera set up on a tripod and point it south, and you take a picture at exactly 12 o'clock every day. And you'll notice that sometimes the sun will be directly south at 12 o'clock. Sometimes it will have not quite reached due south, and sometimes it would have already gone past it. So what will happen over the period of a year is that sometimes the sun will be, at 12 o'clock will be there, sometimes it will be there, but also it moves up and down as we go from winter to summer, and it's higher. And it will actually plot out a sort of figure 8, which is called analemma.
Yeah, that's right.
And the great depiction of that is in the plaza at Bristol Science Centre. First time I went there and saw what looked like spotlights fixed in the ground, and I thought, that's interesting, but what are they there for? And then I realized that it's an analemma. But from that, and from simply measuring the position of the sun in the sky throughout the year, you can calculate that the Earth's orbit is an ellipse, not a circle. You can calculate the tilt of the Earth's axis, and you don't need computers or anything but from that. And it's incredible what you can learn from
It is.
doing simple calculations. So let's have a look in the chat. Do we have any questions in? Not as yet. No, please type your questions. We will endeavour to answer. There must be some coming in. Or is everyone absolutely stunned by what they've heard? Nothing at all so far. Well, well. Alan, do you have anything that you'd like to say?
Well, absolutely amazed at the mathematics that went on there. Sadly, I didn't advance that far with my own mathematics. I do remember the dreaded words of sine, cosine, tangent, and so on. I felt quite, yeah, had been taking me back a little bit there to my school days. But I actually used to enjoy doing the trigonometry with those things when I could remember what they all meant. I always remember OHMS, ohms, opposite over hypotenuse means sine.
Yeah.
Oh my God.
What that means to me now. I remember those tables at the back of the books that we always had to look up this, that, and the other. All I can say, thank goodness Clive Sinclair for the invention of the calculator.
Yeah. Well, somebody's asked a question, what's the furthest object I've tried these methods with? The answer is Neptune.
Wow.
Well, that's pretty impressive.
It is, isn't it?
Yes, I remember my maths teacher, O-level maths, going through sine, cosine, and tangent rules, and sine perpendicular over hypotenuse, and he just came up with some people have come by here to play billiards. As we had a snooker table at home, that was easy to remember.
Yeah, well, I had all those things as well. But what I hope I've shown you here, without really intending to, but I've ended up showing you, is actually there's a reason why they worried about triangles. Because, you know, most geometry really comes down to triangles.
Yes, yes.
And I would say, you know, my day job as an engineer, that's pretty well true as well.
Yeah. And
in fact, Alan Muir is somebody I've encountered during my day job. You did a job for us, Alan, from Tonal Rasak Centre back in 2013-14.
Yes, I remember. Yes, thank you. Yes. A wonderful talk. I've just about to click on.
Are you still there?
Yeah.
Okay, I think that got cut off for some reason.
Hello, Alan, you muted yourself again.
All right. Okay. Do we have any more questions?
The other side of it is, of course, the accuracy of the observation. So when you're measuring Venus, for example, and you want to get it when it is precisely at half phase, well, how precise can you possibly be? So you really, I guess you just have to take lots of readings. And if you take the...
Yeah, with Venus, you get some funny effects because of the atmosphere.
Yes, of course. But if you also take a photo to go with each of your observations, you can then look back at the photos and look through them and say, well, that's when it's...
Yeah, this year with Mars, I'm pretty well doing that.
Yes. Okay. Is there a way to calculate the orbit of Apophis?
Yes.
Well, Terry, I'll put it in
Yes, there is a method.
It's
due to Gauss.
It's not going to hit us.
And the place you want to look for it is in a book, and I'll type in the message to the book. It's Methods of Orbit Determination by Boole. I've got a copy of it here somewhere. Yeah, there it is. Hang on a sec.
Okay. Apophis is a near-Earth asteroid, which is going to come near to Earth.
This book here.
Oh.
Methods of Orbit Determination for the Microcomputer by Dan Boole. And it's published by Wilman Bell, which I'll put in here.
So
you can find it on Amazon or wherever. Sorry, Alan, I keep interrupting you.
Supposed to come by. There's a chance that was touted a few years ago that after that it would come close enough that its orbit will be disturbed to the point that when it next comes round to us in 2029, it might hit us. But we are reformulating the definition of might. It definitely won't hit us.
Well, that's an interesting problem with artificial Earth satellites too. They had two of them collided about 10 years ago. And they hit one another at a relative speed of about 26,000 miles an hour. So that's 10 times as fast as a bullet. That was what made them realize that actually there's an ellipse of uncertainty around the position of every one, because actually they have quite a sophisticated satellite tracking system, and that told them that there'd be a near miss, but they wouldn't hit. And next thing you knew, both these satellites were strewn in bits over an area the size of a continent.
Yes, and of course, the more things there are in orbit around the Earth, the more likely they are going to hit.
Yeah, and I've seen a figure for how many thousand bits they think probably came off those two satellites, but it was pretty scary.
Yes, so whether or not you paint them black, perhaps the idea of putting 20,000 mini satellites into orbit around the Earth may not be a good idea. But that's another matter, isn't it?
Human race is the cleverest and the stupidest.
Yes.
Gary, there's a question there from Richard in the chat list.
Oh, yes, it's come up beforehand. Would your first measurements error be down to using circular motion as opposed to elliptical?
Yeah, I think probably they are. But, you know, it's the difference between a method that you could use at A level and a method that you'd have to be, at the very least, an advanced undergraduate to use, you know, and fairly on top of your maths. And what I was trying to do was just paint with a broad brush and confirm for myself that the picture that we're given as a solar system is broadly true.
Yes. Yes. Okay. Jim Smith asks, have you ever performed any calculations based on observations of our moon?
Oh, yeah. That's right. It was that actually was one of the first ones I ever did. It was that I saw in the sky that the moon and Saturn were close to one another. And I thought, oh, that's cute. Get the camera out, get the telescope out. And Saturn had gone. Well, with the telescope, I could see that it was quite close to the moon, but it was still there. So, okay, so I just handheld the webcam against the telescope eyepiece, shot a bit of footage, and then thought, this is a daft way to do it. Let's go and find a tripod to put the webcam on. So by the time I came back for the webcam, they'd moved apart. And I thought about this for a bit, and I thought, hang on, if I assume Saturn hasn't moved worth a damn in the space of half an hour, I could get the rate of rotation of the moon. Yeah. So I did that, and got a tolerably good answer. So the following month I did it again carefully and properly, and got quite a good answer for both the distance to the moon and the orbital period.
Right. If anyone wants to look up occultations of the moon to various planets, there are tables you can look at, but a fun way is simply using Stellarium. Click on a planet and hit the space bar to put it in the middle of the field of view. Control M will give you an equatorial view rather than a standard view. So it won't the sky around all the time. And then simply get rid of the ground. Press D for ground and A for atmosphere. So you've got a totally black sky. And then just speed up time. And you watch as all the background moves around. And as the moon comes in, then slow it down. You can see whether it passes above or below it.
Yeah. Can you see that? These are those first two pictures I took of the moon way back when. Yeah. Okay. Well, if we go on a bit.
I love your captions there. 2 terrible photos.
Yeah, well, they were. But that's the whole point. You see, what I want to do is encourage people to have a go. You don't have to be super skilled at all this stuff. Just have a go. And go on a bit of calculation. Somewhere here. There we go. There's a month later, right? Over time, there's 118, 125, etc., going down until 212. And the arrow points to a mountain on the moon, which I was using as my orientation point. And in fact, Saturn did go on that night to pass behind the moon as we saw it. There was an occultation that night. And so out of that, what did I get? Similar type ways of doing all the measurements and things. And what did I end up with?
Wow, you can tell this is a spring.
There we go. Worked out due to, the combination of uncertainties. So, there we go. I got a lunar diameter of that, which is, it's about 15% above the published value. And the error in my orbit was about 12%. Somewhere, I seem to have a lot of discussion to get to that.
Earth Moon center of mass. So here we're talking about yes, you're saying that it's not at the center of the Earth.
Yeah, I'm just trying to find out where I got a time. Somewhere, speed.
It's actually just about 1,000 miles below the surface of the Earth. And so although the moon does go around the Earth, because that point is inside the arc of the Earth, it also means that the Earth itself rotates about that point, and so it wobbles in its orbit as it goes around the sun.
I'm trying to find where I got a value for the Earth's, for the moon's orbit period.
Well, I see that this is a USA book as well.
Oh yeah, they all are. And I got told I had to write it in American English, god damn it.
Yeah.
Somewhere I got a period as well. I just can't for the minute see where I wrote it. But it's there somewhere. Anyway.
Any questions coming in? No? Well, if there are none, then I'm sure we would all love to thank Jane for a very stimulating presentation. And some of us, I can practically see Stephen there champing at the bit, waiting to do some observations and measurements, which we will be looking forward to him reporting next month. It's a challenge for you, Steve. Jane, thank you so much.
You're very welcome.
We really appreciated it. I think, hang on, we can, yes, well done, Steve. We have a reaction button. There we go, thumbs up and applause. Thank you. And I'll hand back to Alan.
Okay, well, thank you very much indeed, Jane, for fabulous talk there. And just see if we can get back. I think we should be on to speaker view now. And our guests in Argentina have joined us, so I've just got to find them on our list, and I shall ask Lissandro and Giulietta.
Oh, yes.
Good evening, Lissandro. It's lovely to see you. How's Argentina doing?
Yes, how are you? Everything fine here?
Yeah.
It's around 7 o'clock here in Argentina. And, well, if you want, we can start.
Yes, please.
I can screen share a presentation. Let's do this.
Okay. Yeah, you should be able to share the screen.
Yes.
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 Go ahead.
Can you see the presentation?
Yes. Yes, we're there.
Nice, perfect. Well, as you may remember, I haven't been here the last time, but we are Unicope. Now we will talk about what we are doing, but we have already been here in the group, and we are here to tell you how we are doing, how everything went, and what we plan for the future. So maybe you remember Tomás and Julieta that have been here. Lisandro Acuña is me, Tomás Korenblit, and Julieta González Kratz. We are from Argentina, and we are students at Ford, a school, an international school that is also in London. And now Julieta will tell you what we are doing to remember.
Yes, I'm not sure if you remember, but we are planning to do, what we're planning to do is make astronomy more accessible and reach telescopes to marginalized communities and schools that can't afford them, as that as an excuse to increase interest in science in general. How we will do that? Well, we plan to distribute low-cost 3D printed telescope models similar to PyCon, but without the Raspberry Pi. The Raspberry is the tiny computer that PyCon has that allows it to take pictures, which will make it more affordable. We intend to become a Type B corporation, and for those of you who don't know, it's an environmentally aware corporation whose sales and action help to reduce the carbon footprint. And we have great news. We started working a little time ago on our very first prototype. Thanks to Mark and Alan's help with the distribution of the parts, we now have everything we need to start developing the first version of Unicope and to make 10 telescopes. And really, without Mark, this would be impossible. And our dream that's not only studying the sky, but also help others to do it is now one step closer.
Yes, so we are very happy about that. And for the future, we have already received more than 40 orders of people interested in buying the telescopes for the low cost. That's nice. We have also talked to some governments that are interested in using them. during our summer holidays that we won't have classes, we will have more free time. So we plan to dedicate that time on Unicode, and we intend to launch the first version for the public in the first half of the next year, probably in March or a bit later. So these are the plans, and we want to reach them, as Julieta said, the marginalized communities in our country and everywhere. If you have any questions about Unicode, about our plans or whatever, you can put them in the chat.
Okay, do we have any questions we'd like to Argentina? I think that's very impressive. You've got 45 people already wanting them. I think that's great. Are they from private individuals or from institutions?
No, now they are individuals, but there were some institutions that wanted to use it. But that 45 people are individuals.
Lovely. We've had a question sent in saying, have you marketed your product? And if you have, how have you done that?
Well, Julieta, do you want to talk? Juli?
No, I'm not sure I understood the question, so...
how have you told people about the project and how can they get involved?
Yes, about marketing.
Yeah.
For the moment, we have used social networks like Instagram or Twitter, where we received a lot of followers. There are some hundreds that are now following us. And we won a concourse that you maybe remember. And with that concourse, also the product was viralized a little, but we didn't have marketed like formally the product, investing money. And that's the plan to do that is when we have the product published, so that the people can buy it when they see the promotion.
Good, that's lovely.
Do you have a cost target?
Yes, we plan to, the cost target, it will probably be between $70 and $120, which compared to other telescopes, the same reach is quite cheap. Well, that. And
yes.
Okay, can I ask a question?
Yes.
Yes, obviously.
So, well, first of all, congratulations. I mean, it's an incredible enterprise. I mean, you're obviously busy with your studies as well. So to get this off the ground is remarkable, and it's fantastic. So congratulations. I wish you every success with it. So what about the mount? Because that's often, one of the most expensive parts of any telescope. So what are you doing in terms of the mount?
The what? I'm sorry.
Okay, so the telescope itself obviously needs to go onto a mount, an equatorial mount or an Altaz mount. So are you thinking of supplying that as well?
We are starting to think of the first prototype. Our idea would be to make cost the lowest as we can, would be to 3D print it, but we're not sure if it will work. So we'll try to make a design, try it, and we'll see.
Yeah,
I mean, it's tricky because, sorry, I was just going to say, I mean, you're obviously competing with the likes of massive companies like Celestron and, and Skywatcher and all these others. And a lot of people, a lot of these large companies have small Dobsonian scopes. So it's difficult to actually, compete with these, big corporations. But the fact that you're trying is fantastic.
No, anyway, our idea is not to compete, not to become an international corporation of anything, but to help other people our age, probably amateurs, to have the first gaze at the sky so they can start taking interest in science. I mean, I'm 18 and I've only used a telescope once, and and I'm on the central part of my country. I know of many people who haven't ever done it and want to do it. Our idea is to help those people, those persons.
Yes.
Okay, thank you very much indeed for that. Thanks for the question, Steve. We've got another question here, is roughly how many children will have access to these telescopes? Do you have an idea in mind of how many children you're going to be targeting, or is it more than children you're looking at? Is it the adult groups as well?
Yes, we don't have an exact number, but as many as we can reach, that's our idea. Because here in Argentina, for example, there are schools outside the city that don't have any money and they just cannot see the sky or use a telescope. So those are the children that we want to reach, and they are a lot. But well, we don't have an exact number, but that's something very important to us to use the telescopes in education, in schools, and there are many children will be able to use them if everything goes right. And obviously, adults will also be able to use the telescopes because a telescope is very expensive. And here in Argentina, a third world country, much more. Like very few people can have access to telescopes, and some adults are also interested in them, but they can't afford them. So through our telescopes, the idea is that they can also look at the sky.
Okay, well, it sounds like you really got some good ideas going there. We certainly wish you well, and we would certainly want to keep involved. We're interested in it. It's always good for us to hear how education is spreading, particularly with astronomy. Children do love looking at the sky and looking at the number of people in our club. So do a lot of the grown-ups too. So I'm sure that we wish you well there. And I know our group are very supportive with your project. So we wish you all the best, and let us know perhaps next month or month after that how you're getting on. Okay, well, I think, folks, that brings us roughly to the end of our meeting tonight. So what I would like to do is express our thanks, obviously, to yourselves for all coming along tonight. If you didn't come, there wouldn't be much point in holding these meetings. So thank you for your attendance. I'd like to thank our committee, the group who work in the background to make these events possible. It's hard work putting them on. Everything has to be organised, and so I'm very grateful for all the volunteer support that we get there. So thanks to the committee. And of course, thanks very much indeed to Jane for an absolutely fascinating view about how you can start measuring the orbits of planets. Those of you who have a go at doing it, please send your answers on a postcard to us and we will mark them possibly by teacher assessment, or we will give you an A-level exam at the end of the year. That's it for today. Please make a note in your diaries that December the 9th, Wednesday, second Wednesday in the month, is our next meeting, and the topic is space dogs. Space dogs. Information about that will be on the website in about the next 15 minutes time. So from here in the UK to Argentina and down as far as Somerset in the UK, thank you all for coming along tonight, and I look forward to seeing you again in a month's time. Thanks, everybody. Good night.